The topic today and next week is optimal power flow. This is the menu of today and the menu of next week, and there's a lab associated with it. And at the end of next week, as usual, we will do a small test on all of these topics. I will also mention today pencil and paper exercise that is given in the slides. The solution will be posted tomorrow, so I invite you to do it also to fortify your theoretical understanding of Lagrange duality, which is one of the difficult topics perhaps here. So OPF, optimal power flow, in short, in all detail, the AC OPF, alternative current, so the full OPF problem, is one of the master problems in electrical grids. The problem is we have a grid that is described by an admittance matrix, as we have seen in the previous week. And then we have assumptions that are made on generators and consumers. In the simplest form, for example, we have a forecast or some idea of the consumers, and we want to find what are the set points for the generators. But more generally, we can say that we want to minimize some costs, which is typically the cost of operating this grid, subject to all the flexible resources we have in the grid. The flexible resources, in this context, they are called control variables. They are, in the simplest case, the set point of the generators. That's the problem that energy markets have to solve every day or every hour, practically, when companies like Swissgrid do have forecasts of the consumption of all of Switzerland. And then the job of the market is to make sure that the generators will produce the necessary energy at a cost that is as small as possible. There are other resources, load management actions, this is called demand response, batteries, storage of some form, and then some other more subtle things like capacitor banks that play with reactive power, tap changers that play with the voltage at the output of a transformer. The OPF problem has constraints, so what makes a problem difficult is usually the constraints. So the constraints are, of course, the capabilities of the flexible resources. A generator can produce some minimum power and some maximum power, not more. But of course, the current and voltage limits, and this is what makes the OPF problem an interesting or difficult problem, is that we want that all of those set points are achieved while satisfying quality of service in the grid. The current should be below the ampacity limits of the lines, and the voltage at every bus should be plus or minus within the admissible voltage bounds. Right? We will study this toy example that seems very simple, but in fact is one of the most difficult examples because it's a loop. So let's consider this small grid. In the lab, you will consider other other grids that are more images of distribution networks, but apart from description complexity, we will have all the complexities in this grid here. Here I have a grid with 3 buses, 1, 2, 3, 3 lines as well, and at each of the buses there is a generator, G1, G2, G3, and a load, which is shown with these arrows here. I'm assuming also that the lines are characterized by their admittance here. I do not show here the shunt elements that we know may be important in distribution grids. Here they are not shown, they're ignored. And this is all in per unit, so those are the values of the admittances of the lines. And we have also values of the loads. In this simple example, the loads are assumed to be known. So we want to consume 100 megawatts at this bus, 100 there, and 500 here. And there are costs. The costs are very different. C1 is the cost of generator 1. It's 15 francs per megawatt hour. At generator 2, it's 1, so generator 2 is quasi-free, and generator 3 is very expensive, 225. Right? That's exactly what happens in a grid. Whether the prices are exactly representing the value that we pay for it, or is not clear. Sometimes the price is truly the value, and then if we have renewable energy, if this is, for example, renewable energy, the price per megawatt hour is even zero. Once you've installed a solar panel, the price for all the energy produced by it is zero. Right? If it doesn't produce, it will cost the same. So the cost of generating is zero. So that could be representative of this. Sometimes the costs are also simply the difference between the cost of something that you have already paid and something that you will need to pay in addition. That's the case for renewable energies. It might be the case if you have day-ahead markets, for example. So we have those costs here. We have constraints. Here I'm assuming for simplicity the 3 generators have the same capabilities, and the constraints are written in a very simple form. Here it's rectangular constraints on active and reactive power. Rectangular means I have bounds on the active power and bounds on the reactive powers. In reality, we have more complex constraints. Usually, the shape of the feasible set point is not a rectangle, but to make this thing simple, we take this. Then there are also constraints on the grid here. There are constraints on voltage, certainly. Here I'm focusing on one constraint, which can be expressed in the form of maximum apparent power on the line, which is more or less equivalent to a maximum intensity, line current on the line. Here I'm assuming there's 300 megawatt or 300 megavolt ampere on every line, on line 1-3. So this line here has more transfer capacity than those two. So that's our very simple toy example. Now, given this cost here, the problem is what should be the generator set points here. So the problem can be formulated in, I have to minimize the sum of the costs here, such that, so here voltage magnitudes are within 5%, intensity are within maximum ampacity of the line, and the branch flows are within the maximum here. We can have a more detailed look here. In such a grid, usually one or several of the buses have to be swing buses. They have to be the buses that will provide the instantaneous balance of power, also called the slack bus. In a distribution grid, this is typically the point where a transformer connects you to the main grid. The main grid is supposed to be so large that its voltage is constant and that it will absorb any instantaneous imbalance here. So that's the first concept we see here. Practically for us, from a mathematical viewpoint, it means we assume that this will impose a voltage here. The voltage of bus 1 will be 1 per unit. So that gives us one constraint here that's easy to satisfy. Then I have the apparent power injected into every bus. So those are the nodal power. So S1 is the total power that is injected into node 1. So it is the sum of the power that is generated minus the load plus all the powers that is injected. That's the sum of G1 plus the load here. And by power balance equation, it is also equal to the sum of the power that flows on all the lines here. And we know from admittance matrix equations, from the nodal form of the power injection equations, that it is equal to the complex voltage, so V here stands for complex voltage at bus 1, times the conjugate of the complex intensities that flows out of the node, which is the sum of the currents that flows from bus 1 to the neighboring buses. And by the admittance matrix computation, this depends linearly on the voltage at all the buses here. Right? So the current that flows on line 1, 2 is equal to Y12 times V2, the injected current. Sorry. So this is the equation that we will have for the injected power here, which is also equal by the power balance equation. At every bus, the sum of the powers that get in is equal to the sum of the powers that get out at a bus, at a single point that has 0 dimension, which is also the sum of the power injected by the generator. That's its active power. That's the interesting power. That's the reactive power. We'll talk more about it in a few more minutes. This is minus the loads. And here the load also have a reactive component, which should be specified. In fact, here for simplicity, I'm assuming the reactive power of the load is inductive and has a fixed angle, which is assumed to be known. In reality, it will be varying, but let's assume it will be known. So that's the second constraint we have here. Then we have the constraints on the capabilities. G, the active power and the reactive power are assumed to be within the bounds that are given. The module of the voltage should be also less than minimum and maximum value. The current that flows on line IJ, which is given by the voltage difference times the admittance matrix, should be also given by this maximum ampacity limit. And here, the apparent power limit also is given here. Usually, if we have limit on current, we don't need limit on apparent power, because the physical limit that is really important is the limit on the current. What happens if the current is too large, is above the limit? Why do we care about that? Yeah.
Losses?
There are?
Losses?
There are losses, but we could say that since we minimize the total cost, this will be taken care of by this. Implicitly, here we will minimize the losses. All the power that we generate will be the power consumed by the loads plus the losses. So if we minimize the cost of everything, that includes also the losses. So of course, we want to have as little loss as possible, but this should be taken care of by this optimization criteria. Why do we put it as a hard limit here? Thermal capacity, exactly. If the current is high, there are losses, but also there is heat dissipation. So some things get hot. Right? So when things get hot, for a short period of time, it's okay. If it gets hot for a long period of time, there will be damage to hardware. There will be damage to insulators. The lines will also become longer. They might touch trees, and so there will be a number of unpleasant things that will happen. Certainly, this will also damage transformers if they get hot for too long a time. Why do we care about voltage magnitude being between minimum and maximum bounds? Well, one of them is the quality of service. I mean, if you pay to Romande Energie to get a power service, you assume you will get 230 volts between phase and neutral, right? If you get only 5 volts instead of 230, probably some things will not work. So some of your machines will not work. Some will. In particular, modern machines that are using DC AC inverters very often are able to work through a large range of voltages. But there is a minimum after which it will not work, and also a maximum. If the voltage might get too large, some of the things might not work. A classical example is the elevators. When the voltages become too small, some elevators stop working, which is embarrassing if you have people in the elevator. So as I said, this maximum apparent power is a proxy for that. We will see that in some cases it's difficult to use this constraint, so instead we will use that one. So this is the formulation of the problem that we have. Right? If the problem is of small dimension, an optimization problem of small dimension, I can probably solve it by brute force, by asking MATLAB's fmin_com to solve it. This is what I did here. I asked MATLAB to solve it, and this is possible because the problem is of relatively small dimension. Here is the optimal solution I have found for this specific setting. Here I'm showing in red the electrical state. So this is the voltage. So the state of this grid, as we know from the state estimation lecture, is the complex voltage at every node. So the complex voltage at node 1 is 1 and angle 0 because this is the slack bus. That's the reference node. That's forcing the voltage for the rest of the grid. At node 2, we see the voltage magnitude is 0.98, so 2% less, and minus 26 milliradians. At node 3, the voltage is smaller, 0.95, so we're close to the lower limit, and the angle is much less here also, although very small. Here is the injected power in this bus here. We see the real part is the active power, 400 megawatts. This is what G1 is injected. So with those amounts, it's probably a nuclear kind of thing. Very, very large power here. J is the imaginary part is the reactive power, which is also the max capability that we had here. So this node, the solution, the optimizer has decided that this node should give the maximum it can. Right? For active power, it's not surprising because it might be surprising. The cheapest one is G2 here. G2 is operating here at 235, which is less than its capacity here, and is also having a reactive power component, so it's consuming some reactive power. And node 3 is also generating a small fraction. We see that the reactive power component is non-zero. Why did the optimizer choose to have some reactive power generation here or consumption there? What's the role of reactive power in a grid? Well, if we had only active power, as you may know, from your basic AC course, the power on an AC grid has a real and imaginary part. The only useful work is done by the active power. The imaginary power has an average of 0. It is power that during half a period flows in one direction and during half a period flows in the other direction. So it's useless from the viewpoint of work. So we could say we don't care. It's an average 0, except that, and that would be true if we would be having grids with 0 resistance on the lines. But because there is a non-zero resistance, if you transfer power, oscillating power, then there is always a power loss due to that. So the reactive power causes losses. So obviously, and since it serves nothing, nobody will pay for it. The consumers here will pay for 100 megawatts of each, but the reactive power, nobody will pay for it because in average it's 0, nobody receives it. But on the lines, they will dissipate heat. So we want to minimize, as an operator of this grid, and as an optimizer that tries to minimize the cost of the grid, you will automatically try to reduce the amount of apparent power. And since there is reactive power from 2 sources. There is one generated from the loads. If you remember, in my assumption, I was assuming that the loads are not purely active power. They have a reactive power component. That's typical of all electrical machines. There's another source of reactive powers, which are the lines themselves. The lines have inductance, also sometimes capacitance, or both, or one dominates the other. So in either case, they generate or consume reactive power. So even if you had a generator that produced purely active power, which means the current and the voltage are perfectly in phase, there is no reactive power. Even if that would happen, at the other end of the line, that would no longer be the case here. So the lines cause reactive power. Because they cause reactive power, they increase the losses. One way to reduce that is to compensate by injecting, or here consuming, reactive power into the system. The reactive power also has an impact on the voltage. Typically, we see that reactive power flows in the direction of decreasing voltage, which we see here. Here the voltage is 1. There is a positive reactive power in this direction, which means voltage at bus 2 will be less, and at bus 3 it will also be less. So if we have a voltage problem in a grid, we may also, by playing with the reactive power, change the voltage in the nodes. This all has been integrated in a way that I don't fully understand, because I don't know exactly what MATLAB has done, by the optimization. The optimization is trying to do two things. Reduce the total cost, which will automatically reduce the power losses, which will create enough reactive power to avoid the power, to mitigate the power losses. But it also has to have the voltage within bounds. So in order to have the voltage within bounds, it will also try to play with reactive power. So this is what we see here. We see also something that is called here the marginal cost. What is usually called marginal cost? This is here the marginal cost of consumption at this bus.
The power is the price to pay if you want to produce one more unit of power?
Is the price to pay if we want to here consume one more unit of power. So it's the derivative of the cost, partial derivative of the total cost of the grid with respect to the consumption here. So here, if I want to add 1 megawatt, for example, during 1 hour, so 1 megawatt hour, I will need to pay 69 francs here. Here, in contrast, if I want 1 more, I will need to pay 1 franc more. And here, I will need to pay 226. So we see here at bus 2 that the marginal cost is exactly the cost of local production, which means that the state of the grid is such that if we increase from 100 to 101, then we can simply consume 1 more here that would not change any of the flows. And since this generator is not saturated, it's not producing its maximum, this is the cost that we would have here. Here we see, so the cost is in between, is larger than the cost of production. This is because any consumption here must come from somewhere else, partly from generator 3, partly from this one, but there will be losses also here. Here we see that the cost of generation is larger than the cost of local production, which means probably if we add 1 more megawatt here, it will have to be generated locally here, but this will cause more losses also in the grid. And the fact that there are more losses is visible here. We pay more than 225 here. So this is how the solution is. I redid exactly the same thing by assuming that the capacities of the lines are multiplied by 10. So here, the lines here had a capacity of 200 or 300 megawatt. Here, I multiplied this by 10. And I redid the exercise. What do we see? Yes?
The marginal costs are nearly the same, like 2 francs difference for all generators.
The marginal costs are very different. Here the marginal cost is 15. It was much more before. Here the marginal cost is also 15, close to 15. It was 1 before. And here the marginal cost is 16, close to 15. It was 230 before. So the marginal costs are radically different. The total cost also is very different. So the total cost is 5,000. In the previous case, the total cost was 24,000. So it has been divided by 5 here. So This is because now the grid is able to transfer power from the cheap generator, which is generator 2, to everywhere here. Right? So generator 2, that has a capacity of 400, is now used fully. In the previous case, it was not used fully. The grid was limiting. We had a lot of capacity here. Oops. We have a lot of capacity here, but in the previous case, we were not able to use it. Yes, question?
Yes, the blue arrows, what do they represent?
The blue arrows, they mean that I'm showing at the value, they mean that the value that I'm giving here is the value of the complex power at the beginning of the arrow.
Okay.
So it's minus 30, that means it flows in the reverse direction. Right? There is power, active power flowing from 2 to 1, from 2 to 3, and from 1 to 3. The big demand is in 3. The big generation, the cheap generation, is in 2. So this is what you have in a grid where you have a big city here and a lot of generation here. Cheap generation, for example, you have solar power somewhere that is not in Spain, perhaps, and there's a lot of consumption in Northern Europe. Then if you have a grid that's very powerful, you'll be able to benefit from the cheap production here. If the grid is not powerful enough, then you will not be able. There will be a high price of the grid. So the European grid today is like this. Right? We would like it to be like that, but multiplying by 10 the capacity of a grid means a lot of real estate work. So that's something that is hard to achieve here. Yes, question?
And the cost of replacing the line, was it taken into account?
No, here is the operational cost. I'm not talking of capital cost. So I assume I have a given grid. I have a given commitment of all the things that are in place. I've installed things. Perhaps I've already pre-ordered things that I've already paid. And I'm just asking now, what should I do for the next hour? Given that all of the things I've paid, they are paid and there's no way I can come back to it. Of course, there is another problem, which would give similar type of optimization problems, which are planning problems, where we could say what are the costs of multiplying by 10 the capacity here. But the costs are enormous, right? You can read and so the cost of HVDC lines, for example, between Spain and France, and it's $1 billion or so, right? The costs are enormous. So we'll need other solutions. Then certainly improving the grid where there are strong bottlenecks is one thing that must be done, and that is being done. But there are other solutions, like what? If you have a lot of solar energy here, and you don't have a very powerful line here to transfer it there, what else could you do? Yes?
Store it?
You could store, right? So if we find solutions to storage with pump hydro, that is being done in the Alps, or batteries also. Some transmission operators are deploying batteries or experimenting with batteries to store during the peak hours where there's a lot of energy here to later put it here. Then it becomes an economical planning question. What is cheaper? Is it to invest into batteries, which are expensive, or to buying a line through a continent, which might be even more expensive? What I've shown is a single time step exercise where we needed to do this for a given time slot. Typically, you do it over multiple time slots. And then in that case, you need to take into account the constraints from one time slot to the other. And in particular, there are typically what is called ramping constraints. When you change, for example, every 5 minutes, the set point of a generator, you might not be able to stop and start a big plant at no cost here and within any limit. So typically, there is a limit on the discrete time derivative of the changes in set points. Other than that, from an optimization viewpoint, is the same as we saw before. Okay, time for a little quiz. On this example here, what can we say about power flow and power balance? I'm proposing two statements, A and B. I'm asking you which of those statements are true. If you don't have it installed or running yet, you can go to Speak Up, and the room number is either visible, or if it's not visible, you can use this room number here. Yes?
I don't understand what's the difference between G1 and L1.
So G1 is the power generated by the generator, somewhere between 0 and 400 megawatt. And L1 is the power consumed by the loads, which is equal to 100 megawatt in this example. I close in 5 seconds. And there is unanimity on B, which is true. So B is correct. This is the power balance at a node. The sum of all the powers that go in, which is G1, minus L1. When we talk of the injected power, it means positive is generation, negative is consumption. And then the same thing for the branch powers, because all the power that is injected in the node must go out. So it must go out on line 1, 2 and on line 1, 3. So B is true. And this is one of the equations that we will always find in any power flow equations. A is not true. The power exiting node 1 into line 1, 3, so here at this point, which is this value given in blue here, is not exactly the same as power received at node 3 from line 1, 3. Because there is power loss. There is the active power loss, the heat dissipation on the line will transform. So some of this power will be lost here. And as for reactive power, depending on the line may generate or consume reactive power. So there will also be a difference here. So this is not the same. Voilà, what I've seen is, so far, is what we can say if we ignore the problem of how to solve this optimization problem. So perhaps in 100 years, that would be the end of the story, because the mathematics will have evolved to a point where MATLAB is able to solve it for all cases. Today, it's not the case. Today, the OPF is one of these nasty mathematical problems that is very difficult to solve exactly. So what we will see is how we can solve it concretely, and what is, in particular, one very simple approximation that is very often used, although it's crude, but it's often used, so we will still need to go through it, and also because it gives us some more insight on what happens to the power flows inside a grid. Before getting there, we need to talk a bit about optimization in general. Right? Optimization is divided today into two types of problems, the convex and the non-convex problems. Convex problems, convex optimization problems, are problems for which there is a hope to find a good solver. Some of them are easier to solve than others, but there is some hope that somebody has done a fast solver for your optimization problem. A convex optimization problem is always having only continuous variables. Continuous means there's no integer, there's no binary variables in the problem. Non-convex optimization problem are all the others. It can be non-convex because there are integers or binary variables, or it can be non-convex because the problem, the constraints, or the objective function are non-convex here. And then some of those problems can be solved, and hopefully, as we will see, we can, but it is a difficult problem. And typically, the only way to solve it today is to use heuristics. And that may or may not work well here. What is convex optimization problem? So let's recap on this. It exists in two forms. A convex optimization problem has the following prototype. We have a set of variables, optimization variables, that are constrained such that the set of constraints gives a convex subset of r to the power n. So the variables are real, not integers. And the function to minimize is a convex function. So this is a convex problem. What is a convex set? X being convex means this or not that. Right? A convex set means that if I draw a straight line between any 2 points, the entire segment is in the set here. So this is not convex, this is convex. And what is a convex function? A convex function, the prototype is x squared. It's a function such that the chords, if I draw a straight line from 2 points, I am above the function here. So if I minimize a convex function, so if I minimize something that looks like x squared, over a convex set, I have a convex problem. A variant of this is if instead of minimizing, I maximize, then maximizing requires the function to be concave. So concave is the converse of convex. If I draw a straight line between 2 points of the graph of the function, the line is below. And maximizing f0 is the same as minimizing minus f0. If f0 is convex, minus f0 is concave, and vice versa. We go from this to that by changing the sign here. Of course, there are many functions, and if you take an arbitrary function, it will be neither convex nor concave. For example, the sine function here. And functions like this, of course, will not lead to convex optimization problem. Here is a cheat list of convexity. Well, a first cheat list. This is the formal definition of convexity, which says that if I draw a straight line between x and point at axis x and y, I am above the straight line. This is given by this equation here. If the function is differentiable, an equivalent thing is to say that the tangent is below if I do the order 1 approximation with the tangent, I am below the function, which is given by this here, and which is true in particular if the matrix of the second derivatives is positive semi-definite. So this is a computational method that can sometimes be used to see whether a function is convex here. Then you have all the possible combinations of convex function. If you do a linear combination with positive weights of convex functions, then it remains convex. The max of convex function is convex. The composition is generally not convex, except if we compose with an increasing function. And the level set is convex if the function is convex here. Why am I boring you or spending time discussing about convexity? Well, here is a quick explanation. Why are convex problems so special? Well, if I want to minimize a convex function over a convex set, now here I'm showing a real number. What are the convex sets in dimension 1? They have another name usually. They are the intervals, right? Or the half line. So the only convex sets on the x-axis is either the entire line or half a line or an interval here. So if I minimize here over this interval this convex function, then we see that there is a single minimum, which might not be true always. There might be a plateau, it might be flat at some point. But the key property is that any local minimum is global. So if I have a point where I am locally minimum, so if I'm looking only in a small neighborhood around X, I see all these points I am minimum, there cannot be another minimum somewhere else. In order to have another minimum somewhere else, I would need something like in this function. In this function here is a local minimum, which is not the global minimum here. But if a function has this property, it cannot be convex. This can be shown from convex analysis. So this is why convex problems are so special. Simple-minded methods that like going into the direction of the gradient or in the reverse direction of the gradient will necessarily lead us to a minimum point here. And the minimum point will be a global minimum. So that's why this is solvable. In reality, it's a bit more complex. There are more sophisticated convex solution approaches that have been used here. Here are three problems. Very simple problem. Maximize x squared for x between a and b. Minimize x squared. A slightly more complex problem. Maximize the sum of x plus y over variables x and y that satisfies those constraints. Which, if any, of these problems are convex problems. Okay, let me try again. Is pickup working for you? No, not for me either. So I guess the server is down. So we'll use the good old manual way. Take some time to think about it. Then in a few minutes I will ask who votes for what. Okay, let's start. Who thinks that A is a convex problem? And only A? Okay, not much success. Who votes for B? Okay. Who votes for C? Who votes for A and B? Thank you. Who votes for A and C? Who votes for B and C? Ha, we have a tie between B and C and B only. Who votes for all? None? Okay. Well, let's go through that. Maximizing x squared, well, this is not a convex problem, but minimizing is. So x squared is a convex function. The interval is convex, so minimizing a convex function is a convex problem. Maximizing is not. What is the solution of that? Maximizing x squared over x in between a and b. Yes, but what's the solution of this? Now I'm asking you to do the job of MATLAB. What's the... Yes?
It's x equal to the highest value, so b, or a, I don't know, absolute.
Yeah, it's certainly one of the two. It's a square or b square, whatever is larger. So in fact, a convex function can reach its maximum always at the edge of the domain. Whenever you're in the interior of the domain, you cannot reach. So if a is equal to b in modulus, for example, a is minus 10 and b is plus 10, there are two maximum. And if a is not equal to b, for example, a is equal to 0, is equal to minus 1 and b is equal to plus 10, minus 1 is a local maximum. In the neighborhood of a, we have a maximum. In the neighborhood of b, we also have a maximum. So we have two local maximum, which is not, can never happen with a convex optimization problem. This is not convex, this is convex. Now how about C? Yes?
It's linear, so it's convex.
It's linear, so linear function is both concave and convex. Right. So this function is concave. That's what we want because we have a maximization problem. And we have linear constraints, so if we combine linear constraints, that means we take half planes. If we take the intersection of half planes, it's an intersection of convex sets. It is a convex set. So when we put linear inequalities, we always obtain a convex set. And the linear optimization, a linear cost, also gives a concave or convex, whatever. So max of this is a convex problem. Min also. It's a specialty of linear programs. They are both convex in maximization and in minimization. Is this problem a convex problem? Or is it? Speak up works again, it seems. I close in 5 seconds. And you see the majority answers. That says C, depends on A and B, which is the correct statement. The constraints. What is the shape of the set of constraints? It's a disk, the interior of a circle. That's a convex set. So it's always a convex set when C for any value of positive C. But now the problem is with the objective function. If A and B are equal to 1, x squared plus y squared is a convex function. But if B is equal to minus 1, x squared minus y squared is not. If minus x squared minus y squared is a concave function, but this one is neither concave nor convex here. So that's one of the problems that is often found when we have quadratic problem. Being quadratic, I said x squared is the prototype of the convex function. It is true, but we have to be careful with the signs of the coefficients. If the signs of the coefficients is plus, this is convex. If it's minus, it's concave. And if it's a combination of both, then it is nothing here. So that's one of the problems, that we have lots of quadratic problem, which is what we have in the OPF case, in fact, where we have such things here. Right? Now let me conclude before the break with this last question. The question is the problem formulated? No, which is... Yes, let's do this one again. Right? Another problem formulation. Is it a convex problem? I close in 5 seconds. The answer is obvious. Is B? No, because this is not a convex function as we saw, but also for it's doubly non-convex. The objective is non-convex. and this is also a non-convex set. What is this set? That's the circle. Right? So if we take 2 points in the circle, the chord between the two is not on the circle. It's in the disk, but not on the circle. Here we must have equality. So this is a convex set. It is x between plus and minus absolute value of c. And this is a convex function. It's 2x squared plus a constant here. So that's a convex problem. Why do I go through this for this simple problem? Well, that's because of the take-home message. Whether an optimization problem is convex or not is not something that is invariable by a reparameterization of the problem. So convexity is not necessarily something that is invariant if we change the parameters of the problem. Here I've parameterized the problem differently in x instead of xy, and then bingo, it becomes convex. So some transformation of a problem can lead to a convex formulation. So that's a very important topic, and we will see that in fact in what we have to do in this module and in the next one is first to work on transforming the problem to make it be convex or look like a problem that's easier to solve. Solving problem is not something we do. Either the problem is solvable easily by traditional solvers or not. So we don't in this course go into the simplex methods and things like this on how to solve some specific set of problems. But the work that people will not do for us is to transform our problem into another one, the other one being more tractable for us here. So that's the take-home message. A problem can be formulated in many different ways and it may make a difference. Of course, this asks an important question. What are the problems that can be transformed into convex ones and the one that cannot? Well, the answer we don't know exactly, but certainly we will know that the OPF problem cannot be transformed into a convex problem, at least not very easily. But before getting there, let's look at a special set of problems that we will very often use, that everybody very often use, linear convex problems, when the objective function is a linear function and the set of constraints are linear. This was problem C in one of the quiz we've seen a few minutes ago. All the constraints are linear. A generic linear constraint can be expressed in the form a matrix A times X is less than a vector B, which means for every row of this matrix we have one inequality. So that means this inequality is true for every row of the column vector on the left and the column vector on the right here. And any linear inequalities can be put in this form. If you have inequality in the reverse, say, in the larger than instead of smaller than or equal, then you put a minus sign to obtain this. Here this is equality, so we can have linear equality and or equality, and a linear objective function. So everything is linear here. Then this is always a convex optimization problem. Also if we put max instead of min, as we have discussed before. But beyond being convex, there exist very efficient packages to solve very large-scale problems. So I would say the state of the art in the industry today is to try as much as possible to transform anything that is optimization into a problem of this kind. And then we can solve it for very large scale here. Here is an example, the example we saw in the quiz before, where we had to maximize x plus y over this constraint. I'm showing in the xy plane what are the constraints. So every constraint gives an inequality. X larger than 0 means xy is on the first quadrant. And then those two constraints give the two lines, and the intersection gives the shaded area here. And the maximum point is obtained at the edge here, in fact, at this corner point, this here. This is quite generic for any linear optimization problem. The optimum is never in the middle of the area. It's always at the edge somewhere, and at the edge of the edge, which means at the corner point here. This is why there are very efficient solution problems for that. So we open the box of problem transformation. Which of these problems can be transformed? None of those is written as a linear problem, linear optimization problem. Here we have x squared, and here we have the max of two functions here. The constraints are linear, but the optimization function is not linear. Is there a way to transform the problem to make it a linear optimization problem? So let's see if we can use SpeakUp. I've opened the vote, try to guess. I close the poll in 5 seconds. And we have a Dirac on B, unanimity on B, which is correct here. Let's see why. Because this is an important type of transformation. X squared cannot be transformed exactly into linear things, although approximately we could. We could approximate in some way, but let's talk about it later. Let's look at the max here. Problem B is minimizing a function which is the maximum of two things, x plus y and 2y here. Then a trick that is very commonly used is the following one. If I have to minimize the max of a number of expressions, is the same as minimizing t, so I add another variable. I augment the number of variables of my problem. I add a t, and I say I want to minimize t, and I add as constraint that t is larger than all the functions that occur in this maximum expression here. So t is a variable that is not in any other constraint, so it's independent of all other constraints on x and y. And then it's easy to see that if you fix x and y, and you reason about, for a given x and y, what value of t reaches the minimum? Right? What is the value of t that reaches the minimum of those two things when x and y are fixed? Well, the smallest t that's larger than a and b is the maximum of a and b. Right? If you impose that t is larger than a, t is larger than b, and you want t to be as small as possible, you have to be as large as the largest of the two. If a is larger than b, then you want t to be equal. So if x plus y is larger than 2y, for x and y fixed, the minimum of t it would be x plus y. And if it's 2y that is larger, it's 2y. So in general, the minimum of t over this is the max. So this is why that this change here is equivalent to the problem we had before. In the solutions that I will post later, we give exactly a formal proof of the two. But the intuition, I gave it here. Finding t for x and y that is fixed. When x and y are fixed, finding t that minimizes the max, that minimizes t subject to those two constraints is the max of the constraint here. And this is quite general, and we have to learn how to do this transformation for general problem. If I have to minimize a function which is the max of another set of other functions, this is equivalent to minimizing t over t larger than set of function plus all the other constraints here. So this is a general statement that we can do that can transform a problem that has a max, which is a highly nonlinear operator, into a problem where there is no max that is written. Second, we can use this trick by approximating any convex functions by a max of linear functions. If I have a convex function here, x squared, for example, a convex function has the property that the tangents are always below, and if I put as many tangents as I want, so a large number of tangents, and I take the max of those straight lines here. The max is whatever is above here. Then I will have a line which is not exactly the function. Here there's a small difference between the function, but is an approximation of the convex function. So any convex function can be approximated by its tangents. And if we take in the limit an infinite number of tangents, you'll have an exact thing. If you take a finite one, you will have an approximation whose quality can be as good as you want by putting as many lines as you want. It's the same trick as if you have a circle, you want to draw a circle, you don't know how to draw it, you can draw it with 16 lines, for example, that will give you something that is a very coarse circle, and if you do it with 256 lines, it will already look like something that is a good approximation. So f0, this convex function, for example, x squared, can be approximated by the max of linear function, which means that the problem here, if I approximate this by max of linear functions here, I do it for this and for that, then I can approximately make it a linear program here. So this is one of the tricks that's very often used when we have squares and it's embarrassing. Then we can replace it by a linear program here, right? As we saw here. Last question to check this understanding. Here, I'm giving a problem P, which is absolute value of x minus 1 minus 5. I have to minimize this, so that's the L1 norm, the distance between x minus 1 and 5, but not the distance with squared, or the Euclidean distance, the L1 distance, subject to this linear constraints. And I'm saying this is obviously not a linear program because of the absolute value, that's nonlinear, but I try to transform it in this or that. Is any of the two equivalent to P? I close in 5 seconds. And the majority says A, which is the correct answer. Because the absolute value of something is the max of two things, is the max of something and minus something. Here, P and Q cannot be anything for lots of reasons. But certainly if P and Q is very large, if you consume a lot of active power on a given line, what will happen if the consumed power is huge? Something bad will happen, something undesirable. The current on the line may be too large, so we might violate the ampacity limit, or the voltage will typically drop. If I consume a lot of power, typically there will be a drop of voltage here. Here, I'm assuming the line ampacity limit is very, very large, but I have constraint on voltage magnitude. For a given P and Q, the generator that is the slack bus will compensate whatever power is required. So the generator will generate the P and the Q plus the losses of the line, the active and reactive losses of the line, which are entirely determined by P and Q. So this is the only control variable. But we have these constraints here. Those constraints, I can compute them by doing a load flow. Right? The load flow will tell me if I inject PQ in this simple grid that has only a single PV node and a PQ node, what is the electrical state that will give me the voltage here and the power there, doing the load flow, Newton-Raphson, for example. So for every value of PQ, we'll have a given voltage, and I'm asking what are the values of P and Q, all values of P and Q, such that the voltage lies between those two bounds, plus or minus 5%, which are standard operational constraints we put. Here, the solution is plotted here in per unit values. On the y-axis, for some reason, the electricians put P on the y-axis and Q on the x-axis. The blue part are the unfeasible points, and the red parts are the feasible points here. So there is a very small shape here where it is possible. If P becomes very large, then the voltage drops, but it depends also on the reactive power. You can compensate if the reactive power is 0. We see there is a very small fraction where P is admissible. If I increase P, if P consuming means P negative, if I increase the consumption, I can compensate the power drop by injecting injecting reactive power by having a positive Q, but this will go only to some limit here. This is not a convex set, obviously, right? And there are many problems where it will not be able to transform an optimization problem over this set into a convex optimization problem. For example, if the objective function is a linear function of P and Q, and if the coefficients are such that the lines where the objective function is constant is, for example, a vertical line, we see that there will be two maxima that are, and there might be local maxima or local minima that are in one area or the other here. So this is showing the problem of the AC optimal power flow. We are working on sets that have this shape. Of course, in reality, things are not as simple as this and not easy to visualize, because even in a single line, we will be three-phase typically, so it will be in dimension 6 and not 2, where I stop being able to do nice graphics. And there will be not just one node, of course, but a few thousands of nodes in any network, so we're in dimension several thousands. But it has been invariably found that we always have this problem. We have a non-convex problem here. So what do we do? Well, we'll see two things that can be done. One is an approximate solution by iteration, that it will be more accurate, but we're not able to say much about it. Let's start with something that is a bit crude, but very easy to reason about, and is used routinely, for example, by the market clearing mechanisms for energy in Europe and in other places in the world. This is based on what is called the DC approximation of OPF. Right? What is the DC approximation? DC approximation does not necessarily mean that we replace the grid by a DC grid. We do keep a DC grid, but we observe a number of things. On transmission networks, so very high voltage lines, Swiss grid, for example, the 100,000 volts and beyond, the resistance of the line is much less than the reactance. So the reactive part of the lines is much larger than the resistance. The resistance is non-zero, but its effect is much smaller. Right? Also, it operates in a region where the voltage magnitudes are very close to 1. And the voltage angles between the different buses are typically very small. We found here milliradians, sometimes hundreds of milliradians, so we never go much beyond that, and often much below here. So we say the resistance is much larger than the imaginary part of the impedance of the lines, which also means that when we take the admittance of a line, which is 1 over the impedance, the same will be true. So the real part of the admittance, which is the conductance, is much smaller than its imaginary part. So why do we care about the admittance? Well, because when we write the power flow equation, that's much more convenient with the admittance. So the admittance writing of the power flow equations are this: the power flow on line KL measured at the departure of node K, so this value here. Remember, it will not be the same at the other end because there are losses in the line. Here I'm also assuming the most general line model, where we have shunt elements here, is given by this formula here, where this is saying that the power flow is equal to the power flow that goes into the longitudinal element minus the power flow that goes into this line here. Now, if we do the maths, we introduce the admittance of the line here, we obtain at the end this formula, where the star means conjugate here. These are all complex numbers here. If we are interested only in active power, in the DC approximation, we model only the active power. Other questions on this here, on this formulation?
Just wondering if the resistance was the real part of the impedance or the admittance?
The resistance is the real part of the impedance. So when we do 1 over Z, what do we obtain?
The conjugate?
We obtain, well, let's do it. We will. So Z is R plus JX. The admittance, Y, of the line is 1 over Z. And the inverse of a complex number is the conjugate divided by the module square. So it's R minus JX over R squared plus X squared. So if R is much smaller than X, R over R squared plus X squared is much smaller than X over R squared plus X squared. In fact, the ratio of the two is the same. It's perhaps counterintuitive, right? When we take complex numbers, we take the inverse. The ratio of real to imaginary part is the same in absolute value for Z and 1 over Z. So in practice, G, which is here R over R squared plus X squared, G is much smaller than B here. So this is where we are. This is an exact expression. And here we will say that, therefore, if we're interested in the active power flow, the active power flow is the real part of all that stuff. So here there's a pure imaginary thing, so we can throw it away. So we see that the shunt elements don't play a role in the active power flow here. So the active power flow is simply given by this formula. Right. Now we will do the following assumption. We will set G to 0, because we assume it's much smaller than B here. We will also assume that the modulo of V is equal to 1 and that the angles are small. So modulo of V is equal to 1. That means when we will have V times V conjugate, we will replace by 1. And we will do, this is, you recognize here the power series expansion of exponential. Exponential something is 1 plus x2 over factorial 2, etc. Here we say if theta is small, the following terms, which are theta squared divided by 2, theta cubed divided by 6, etc., all those numbers can be neglected. Therefore, we approximate by this, which means the cosine is approximated by 1 and the sine by theta. If we put all those things together here, if we put the approximation here, this is the exact value we have. The module will replace by 1, the exponential by 1 minus j theta, and when we number crunch all of this, we obtain this thing here, and when we take the real part, we obtain this very simple expression. It's equal to minus b, where b is the imaginary part of the admittance, times the difference in angles here. Right. So b is very often negative, so minus b is a positive number. If we call it capital B, we obtain this expression here that says that the power flow between K to L, the active power flow, as first order approximation can be approximated as B, the imaginary part of the admittance, the minus it, times the angle difference here. This is the DC approximation here. It's very useful because it tells us in an AC grid, a typical high voltage AC grid, the power flow is simply proportional to the angle difference. So we see that the thing that matters to know where power is flowing is the angles, the complex voltage angles here. Therefore, the injected power will be simply given by the sum of the, so this is the total power that is injected by all the systems that are connected to node K, is simply equal to the, by the power flow conservation, by all the power that flows into the lines. Also, since in the DC approximation we ignore power losses, the sum of the powers at every node will be equal to 0. Right? We ignore the power losses because the power losses correspond to the quadratic term in the exponential thing that we've seen before. So this is the DC approximation for a grid here. As we see, it's fairly crude. It ignores completely the power losses, but the benefit is it's completely linear. We see that if we take as state variables the angles, we have powers that depend linearly on the angles. Let's do it for the toy example that we've examined an hour ago. Here is my grid with the admittance that are given here. We see here that the real part of the admittance, which are, for example, 1.8, is smaller than the imaginary part. Not much smaller, so DC approximation doesn't require the real part to be minuscule, but just one order of magnitude smaller, approximately, which is what happens here. Those are the expressions I obtain. So P1, the power, active power, injected into node 1, is the sum of the power that flows onto line 1, 2, and 1, 3. On line 1, 2, we have the imaginary part of line 1, 2, which is 22.19, which with 3 digits of accuracy, I approximated as 22.2. So this is, for this line, it's 22.2. The angle difference, theta 1 minus theta 2, plus 11.1, because this is the imaginary part of this line here. So we write this for those 3 lines, and we obtain this here. We can also see that if we sum up all those equations, equation 1 plus equation 2 plus equation 3, we will obtain 0 on the right-hand side. On the left-hand side, we'll obtain P1 plus P2 plus P3. On the right-hand side, we will obtain, if we look at all the coefficients of theta 1, 22.2 theta 1 here, plus 11.1, and here minus, where is theta 1? Minus 11.1 here, minus 22.2. So this equation is in fact redundant. It can be derived from the 3-1 here. Or, to put it differently, out of those 3 equations, if I add the power balance equation that ignores the losses, we have rank deficiency. We don't really have 4 equations. Fortunately, because if we reason in terms of load flow, a load flow is considering here, give me the powers, the injected power. If I consider that for a load flow, I need a slack bus or some kind of swing bus. So here, if I assume node 1 is a slack bus, that means is the one that does the power balance. Whatever P2 and P3 are, node 1 will balance it. So node 1 will do P1 that is equal to minus P2 minus P3. So my 3 variables are P2, P3. And given P2, P3, the electrical state of the network is the angles, theta. Theta 2, theta 3, and theta 1. But since node 1 is the reference bus, theta 1 is 0. So the electrical state of this network in this approximation is given only by theta 2 and theta 3. So I'm doing a very simple load flow here, an approximate, a caricature of a load flow, if you want, a very simplified load flow, where I obtain theta 2 and theta 3 from those equations. Of course, I have only 2 variables, which means that out of the 3 equations, in fact, one is a linear combination of the other. So I can eliminate the third one. I have 2 equations. I can compute theta 2 and theta 3, setting theta 1 to 0, and that will give me the electrical state here. We are interested, for example, also on the branch flows here. Then we can obtain them by using the equations that we've seen before. So that leads to this approximation of OPF, where we minimize the sum of the power, active power, over power injections, electrical state, which are the angle, line power flows, that satisfies the different equation that we've seen before. So those are the equations we just saw on this grid. That includes the equation for the branch power flows, plus, of course, any additional constraints we have on the capabilities here. Here, we have lost a few things compared to the full ACOPF. For example, we have lost any constraint on reactive power. We're not assuming anything on reactive power. It disappears from the equation. We've lost also the power losses because we assume the sum of the power is 0. And any constraint on voltage is assumed to be automatically satisfied because we assume all the voltage magnitudes are equal to 1. So the only thing we can capture is the active power flow on the lines, which must be bounded by some maximum here. So again, this is a very simplified thing, which is fairly accurate if we don't want to know what are the losses, for example. But the beauty of it is, of course, that everything in the constraint here is linear. So if we take a cost that is a convex function of P, then we have a convex optimization problem. I did it for my toy example. Here are all the equations I obtained. Those are the equations we just saw a minute ago. P1, that was the injected power into node 1, now it's G1 minus L1, etc. Those are the branch flow equations, branch power flows on line 1, 2, on line 1, 3, on line 2, 3. I'm assuming that they are maximum, they do not exceed the maximum branch power flow. Of course, here I'm ignoring the apparent power. I'm assuming the active power is the apparent power in the limit here. In this problem, what are the control variables? They are the G's, G2, G3, G1 if we want, but we have this equation here. L1, L2, L3 are parameters. They are assumed to be fixed. I know the loads and I want to find what are my generation sets. Then I have these additional state variables, the theta and the capital P, which are the branch power flows that are additional variables that I have to consider. I solved it. Now it's very simple. Because it's a linear convex problem. Here I assume linear cost because the cost is simply fixed at every generator. Here is the solution I find. We find branch power flows that are now pure active power. We see that they are not very different from the values we had obtained with the full ACOPF. Fortunately, because this is how European markets work for deciding what are the optimal values of generation. Of course, we have ignored the losses. So once I've done a DCOPF and I've decided, okay, I will do this and that, we still need to reincorporate the losses. So the way this is done in electrical markets is to do a load flow from the generators. So we say, here are the generations here. We will compute the losses, and then we will need a bit more generation due to the losses, and this will be reattributed as a flat tax to everyone. The tax to be able to use the grid is to pay for the losses here. We see that the marginal costs are also very close to what we found. Not exactly here in this case, but very close here. Here, since there is no loss, the marginal cost is exactly the production cost at this node here. Before, with the ACOPF, it was a bit larger. And we see similarly that if we increase the capacities, the power flows change dramatically. Now we see that we don't generate anything here. We see G3 is equal to 0. I put a JQ, but there is no Q. Q is always equal to 0. And they are again very similar to what we had obtained with a full AC power flow. This allows us also to understand what happens in a grid, right? We could say here, why do we need, for example, when G2 is sending power to G3 here, G2 is the cheapest here. That's the one that's producing at full power. And we see there is a negative sign here. So some of the power of G2 is going via G1 in order to reach G3. Whereas here the capacity of the line is not saturated. We could reach 300 here. So why do we do this? Well, that's because of the law of how power flows, right? In a power grid, we cannot decide individually on the power flow on every line. We cannot say, I want 300. If I could decide on the power flow on every line, I would put, because on the line 2, 3, we have a huge limit here. So I would put all the power here. I don't need to transit some of the power via node 1 in order to reach 3 here. I would do that if I could route the power as I want. But I cannot route the power. It's not like packets in a network where I can decide by a routing table where the packet goes. I do not. How does the power flow? Well, in this DC approximation, it flows by following the angles. The only thing you can control is the angle. So it's similar to a water hydraulic network, where the angle plays the role of the altitude. So you can imagine that node 2 here is at a given altitude, which is given by this, plus 18. Node 1 is at altitude 0, and node 3 is altitude minus 216. So if you put some fluid here, in order to reach there, some of it will flow here because G1 is below. And there's no way you can avoid that. So you cannot control the power flows individually. You can control the voltage in angle, if we have the DC approximation, in reality also in magnitude. And power will flow from higher voltages and higher angles to lower voltages and lower angles here. So this is the only thing we can do to control a grid is to control the voltage angles and secondary also the magnitude. Voila, so that's the interest of the DC approximation is that it's tractable, so we can do very simple things with it. Also gives us a fairly simple explanation of why power is flowing when the approximation is valid. The approximation is valid in very high voltage lines, so typically transmission networks. The transmission networks are the backbones of the countries. Every country or every area in a country has one transmission network that's under the control of one transmission network operator. And then you have zillions of distribution networks that are under the control of municipalities or other operators. In distribution networks, the resistance components of the lines are often important, so we may not be able to use the DC approximation in distribution networks. We've seen that we had typically to do the kind of optimization we do with DC approximation, not just with one single time slot, but multiple time slots. And that led to what is called ramping constraints. This we've seen already. But in addition, typically we also have non-linear elements that are due to startup costs. If I have a generator that is not working at all, and if I want to start it, there is a cost. So the startup cost here is related to a binary variable. So assume I have to do the problem over the next day. So one time slot is 1 hour. And assume I have 3 generators, like in my node here. And I need to decide at every time slot which generator is on and off. And assume that I have a startup cost here. So a startup cost is a cost that I pay if the generator is on and it was off before. So W is a binary variable that says whether it's on or off here. Similarly, I may have a start down cost. To stop it, I need to send somebody to do something that will cost some money. And so I may have similarly a start down cost here. So that's the real stuff we need to solve. Is this a convex problem? If we do the DC approximation, yes? No. It's not a convex problem because of those things here that are binary variables, right? They're equal to 0 or 1. Binary variables means we're introducing something combinatorial into the problem. If this would be an integer, well, we would have this quadratic term that is also non-convex here. So this is not convex. It has a combinatorial problem into it. So it will not be as simple. However, the state of the art today is if we combine a linear program, so not just convex, but purely linear, with a few a few integer constraints, like I was doing here in the previous slide, then there are efficient heuristics using, in particular, the branch and bound heuristics. So those are heuristics that are trying to find as good a solution as possible, and that are able to know whether, when they have found a solution, it is guaranteed to be optimal. And if it's not optimal, it is at least good here. So take-home message is, even if the problem is non-convex, but is a combination of linear problem with a few integer variables, so what is a so-called mixed integer linear program, if the number of integer variables is not huge, there is some hope of being able to solve it efficiently. Fortunately, because this is what is called the unit commitment problem. If I have to decide for the next day in advance when and which generator I will start, I have typically this problem here. So in the lab, you will be able to check whether what I'm saying is true, whether it really works in practice here. Let's conclude this section with a few wrap-up questions. With the DC approximation, what statement is true? I close in 5 seconds. 10 seconds. Okay. Ta-da. And by a short distance, D is winning, which is the correct answer. So the line resistance are taken to 0. The voltage magnitudes are set to 1. This is correct. Of course, the voltage angles are not set to 0, otherwise there would be no variable. Incidentally, we can wonder, whoops, no. This is, so the answer is D. Now let's conclude with yet another quiz. This one. The true final quiz of the day, of the hour. Close in 5 seconds. I should open first. Do you see anything on your? No, I don't either. So let us let us use what one learns after a PhD in computer science, which is kill the process, reboot. Voilà, it should work. I close in 5 seconds. A is true because of B, in fact, there is no power loss in the branches. So at two ends of the line, we have the same power flow, and of course they have the equal magnitude, different sign, but equal magnitude. Now C, we might wonder if it's called the DC approximation, is it because it models a DC grid power flow here? And the answer is yes and no. No, formally. The power flow equation in the DC grid are quadratic, right? In a DC grid, we still have a quadratic problem. The DC approximation is called this way because it's similar to the laws that relate current to voltage. So voltage takes the DC voltage takes the role of the voltage angle, and the current takes the role of the power flow. So if we reason as an AC grid, as a first approximation, we have the same behavior as a DC grid if we think of the power flows as currents in a DC grid, right? Which might be a useful way to imagine what can happen in the grid. But certainly it's not the DC grid equations are, in terms of power flow, are equally bad as the AC grid equation, right? They're quadratic and hard to invert. Voila, we do a break. Long overdue. So let's resume at 11:25. We have seen the first method, which is very simple and has a lot of advantages. There are many other methods for doing optimal power flow. One of them is a brute force. So if you need really to find an optimal power flow for starting from no information, then you might still use a non-linear, non-convex solver. This is routinely done also by network operators. But there is another method that is often very useful. It is when we want to start from an exact operating point of the grid and we want to find an optimal that consists in perturbating this point of operation. This is, for example, when we do real-time or quasi-real-time control of a grid. For example, if you have a grid in which you have mechanisms for voltage control, this is motivated typically today by solar panels. When you have a lot of photovoltaic resources, they tend to create voltage problems. So you may have resources in the grid that are able to change the voltage by injecting or consuming reactive power. But then you need to change their set point once in a while, every 15 minutes, for example. This is what we could call quasi-real time. For such cases, we start from an operating point and we want to find an optimal that's not too far from a region where we are. So we are not solving a problem from scratch where we have all the power injections and we need to find the optimal point, having no idea where it will be. Here we want to do small changes. In that case, a very frequently used method is based on iteratively linearizing the problem. That's a problem very used in control theory for Kalman filters, for optimization problems. There has been decades of control theory that work well with linear systems. We know how to linearize a system by using its first order Taylor expansion. So if we combine the two, we obtain what is called the sensitivity coefficient method. So what is it? Well, if I have a generic grid here, and I have simply, I can write in a compact way the injected power into node I versus the complex voltages in all nodes using the admittance matrix Y, we can write this in complex form by saying that the injected power are a function of the complex voltages at all the nodes. Here, I'm taking all the nodes, assuming there is one slack bus. So the slack bus complex voltage is complex number 1, so we ignore it from this. And the load flow problem that you have studied in the previous module is to invert this mapping. Given S, find V, for example, here. Now, to do this optimal power flow approximation, we will do a linearization of these power flow equations. Linearization means if I have an operating point, V hat, S hat. This is, for example, something measured. We know now the complex voltage and the complex power injections because we have measured them. Then for points that are not too far from it, we can say this. Now what does that mean? This is a vector of complex number or rectangular coordinates, which is equal to the point at which we are, plus the gradient of this mapping F times the increment V minus V hat. So that's a very compact form of writing the power series expansion at order 1 here. It's multidimensional. V is a vector, S is a vector. V has the same number of dimensions as S. So gradient of F is in fact a square matrix. Right? It's also called the Jacobian matrix, or the differential of F. Right? Now once we have done that, and once V hat is fixed, then we have a linear problem. We're just pretending that S is equal to this linear thing. So with the DC approximation, we had a linear approximation. Here we have another linear approximation that is more accurate, will include also reactive power, losses, everything, but is accurate only in a neighborhood of a given point, V hat here. Concretely, in matrix form, this would give something like this. I'm writing the injected power. There are many ways to write it. We can write it in rectangular coordinates. That's what I did. Even if you use rectangular coordinates, you can choose whether you put PQ together or all the P's together. I chose here in this way for compactness of writing. So this is my vector S, written in rectangular coordinate. This is my S hat. And this is my Jacobian matrix. So what does it mean, the Jacobian matrix? Here I'm using for the complex vector the polar coordinates here. Polar coordinates mean I use the modulus of the vector, which is the voltage magnitude, and the angle here. I could also use rectangular. I could use the real part of the complex voltage or the imaginary part of the complex voltage. It works as well. Very often this works better because when theta is small here, V is close to 1 and theta is close to 0. So that gives things that are often better accuracies, that give better accuracies. So if we use this, then the matrix here, that's the differential of F, is given by all the partial derivatives. For example, on the first line is what gives me the active power injected at node P1. Then it's a linear combination of this times that. So if we analyze, it means the active power injected at node P1 is dP1 over dV1 times V1 minus V1 hat. So it says if the voltage varies, magnitude varies by this amount, then I need to multiply this by this coefficient. So this coefficient is the partial derivative of the active power at node 1 with respect to the voltage magnitude here. In the DC approximation, we ignore that because we assume the voltage magnitudes are all equal to 0. In this method here, we do not ignore it. And similarly with respect to the angle, and similarly with respect to reactive reactive power, so the imaginary part of the power here. So that's the very traditional form. We use usually active and reactive power because those are things that make physical sense, and we use very often voltage magnitude and voltage angle. Right? Then once we have that, one heuristic is called sequential linear programming, It consists in doing the local linearization iteratively. So we solve the problem, minimize the costs of everything. So the cost of everything is typically the cost of the power injections. Sometimes also the electrical state. So V is a shorthand notation for the complex voltage, which is the electrical state. And this may include, for example, a penalty for voltage magnitude being too far from the nominal value. We may or may not have a component here. If we can also linearize the voltage magnitude using the differential in a similar way. So this can become a linear function, or at least with respect to V, can be quadratic with respect to the cost here, to the injected power. And then once we have done this linearization, the S equal F of V is a linear. The load flow equations that we wrote, that we saw in the previous slide, are now linear. It is this. This is S equal F of V. This is V, this is S, and everything is linear. We also have linear constraints typically on the powers and electrical state that may be due also to voltage and current magnitude. We can have them in the cost, we can have them in the constraint. We can often have them both. For example, we may want to penalize the operation in a region where the voltage is between 0.95 and 0.97. We don't like to be in this region, so we put a penalty for being there, but it's not a hard constraint. The hard constraint would be we must be above 0.95. So we may have both, depending on how we want to make the problem tractable. So this is one linearized instance of the problem, and then the iteration works as follows, right? So we do repeatedly. We solve the problem starting at an initial point. So we start with sk minus 1, which is S0, which is where we start from. So we start from the operating point where we are now. In some other case, we start from another approximation, for example, the DC approximation, completed with a load flow. Then for every k, we find an optimal point. So we have linearized the system here. We find an optimal state, V, and an optimal set of injections. Now this optimal state and the injections, they don't satisfy the exact power flow. They satisfy only the approximated power flow equations. So they may not be exactly feasible. So we need to iterate until we hope we reach a fixed point. So at the first iteration, I find a new optimal point, S1, V1. I take that as starting point, and I solve again the optimal problem where I find S2, V2. If I am lucky, and in practice, if we don't do large changes to the power flow set points that we had from the previous iteration, this will converge. And if it converges, then we stop. If we converge exactly, it means that Sk is equal to Sk minus 1. Since Sk is equal to Sk minus 1, then the power flow will be exact, because the power flow equations are exact at the point at which we linearize. Right? When I do this here, at the point hat, the power flow equations are exact here. So, whoops. This is called sequential linear programming. It's a recipe that is used in practically any area where we have to solve non-convex optimization problems. So one trick is to make it convex, in fact linear, for all the constraints here, solve it iteratively, and hope that it converges. It may or may not converge, depending on the problem. If you solve a big grid problem and you have no good initial point, this may not converge. But if you start from a modest grid problem and you have a good initial guess, the practice shows that this will converge. So you will be able to experiment this in the lab here. when we look at those different linearization here, we may need to do things like we may also want to linearize the voltage magnitude, for example, with respect to the power. This can be useful if we want to express, for example, voltage constraints here. And the classical way to do this is to invert the previous relationship. If I look at this relationship, right, this is saying that the vector P minus P hat is equal to this big matrix where this is V theta minus V hat theta hat. Right? So that's a big linear inequality. I can invert it if this matrix is invertible. Right? This matrix is invertible if we are at a non-singular point of the grid. Singular points are points where there is what is called voltage collapse. So when you reach a singular point in a grid, something bad will happen. So typically, we operate far from those points. So if we are not at one of those points, this matrix is invertible. And if I write the inverse of the previous relation, we obtain V theta minus V hat theta hat is equal to the matrix inverse times the S minus S hat here. So this can be useful for expressing the voltage constraints, for example. This has a name. The coefficients of this inverse matrix are called the voltage sensitivity coefficients. So one way to obtain them is to compute the Jacobian matrix by writing the equations, writing all the derivatives, computing the derivative, and taking the inverse here. Be careful that the inverse, if you observe what I wrote here, I wrote the big matrix minus 1, right? Which is not the same thing as the inverse of this coefficient, right? The first coefficient is not dp1 divided over dv1 inverse, right? As you may remember from analysis 103, the inverse of a partial derivative is not the derivative. I mean, dv1 over dp1 is not dp1 over dv1. You don't. It's the full matrix that you need to invert, right? So to find one coefficient, you need all the coefficients here. They are called voltage sensitivity coefficients, and they play an important role in the constraints and in general in solving optimal power flow in practice. This is why also this method is called iterative method with voltage sensitivity coefficients. Right? Quick question. What is 2?
I think it's the...
It's a few slides before, yes. Yeah. It's 2 is the linearized equation where we use the Jacobian matrix. Right? I close in 5 seconds. And the correct answer is both are true. It applies to AC OPF, that's the goal. And it replaces the load flow inequality constraints by this. Right? So you replace the grid equations, which are source of non-convexity, by a local approximation, which is convex. But of course, the price to pay is you need to iterate because the solution you find at every step is not satisfying the exact power flow equation, so it's not a physically feasible point. But if it converges, it will work. Let's skip this. You'll be able to look at it when I post the solutions. Let's move on to the next point, on which we will conclude for today, the concept of Lagrange multipliers and their application, which are called locational marginal price. In the electricity market and in the operation of transmission grids, this is the basic a basic mechanism that is used. We have seen in the two examples at the first hour that depending on the transmission capacity on my toy grid, that I had different marginal prices of power at every node here. So European markets are evolving towards introducing this in the electricity market, where the price of energies in a given part of Europe will depend on exactly those prices here, which is called locational marginal prices. So it's, by definition, is the variation of cost when we increase by some small amount the demand here. So this is used to define what we call supply curves. We'll see that when we do a theory of demand response in the next module. And this is used for running transmission grids in Europe or other large interconnections here. And they are based on Lagrange multipliers here. So what we will do now, before we conclude for today, is a crash reminder on Lagrange multipliers here. So Lagrange is something very simple that whenever somebody has to solve an optimization problem with constraints, they say, okay, let me write the Lagrangian, solve for it, and etc. But I found personally, by reading all those papers, that there are lots of questions. It's not so easy. And all papers don't do it the same way. So I did a bit of research on that. And I found that the most widespread and the best book that exists today is this one. So one of the difficulty in Lagrange duality theory is that the same theory is presented in slightly different ways. And depending on the authors, they're all equally correct, but you have to pick one. And since this one is very well written and very well and very complete, and also very concise, it gives as few details as is strictly necessary. So to go into this, we need first to a simple way is to have what we call a standard form. So every textbook will have a standard form of an optimization problem. The problem is that all standard forms are not standard. So everybody has their own standard. So here is the one used by this textbook that I recommend, Boyd and Van den Berg. So we will strictly stick to that. So any optimization problem is put in this form. Minimize. We've seen we could minimize or maximize, but we will minimize a function f. Often f will be convex. So we're not necessarily talking of convex problem here, although very often it will be the case, but not necessarily. Subject to inequality and equality constraint. And we decide that the inequality are always negative, less than or equal. So that's the standard form. Of course, it's completely arbitrary. I could put larger than or less instead of less. I could also delete the equality because an equality corresponds to two inequalities. But that's a convenient way to write the form. Some terminology. A problem in this general form may be unfeasible. Unfeasible means what? It means that there is no value of x that satisfies the constraint. If there is no value of x that satisfies the constraint, then the problem is said unfeasible. If it's unfeasible, by convention, the optimal value is plus infinity. Right? Why plus infinity? Well, that's a convention that works. The minimum of an empty set. Now, if the problem is unfeasible, the set of all the values of f of x is empty. And the minimum of empty set is plus infinity. Because that's a neutral element. When you take the minimum of something and infinity, you can ignore the infinity. So that's a convention. It's important to remember it. We'll see it plays a role in duality with linear programs. Now, if the problem is feasible, that means there are at least one x, and hopefully many x that satisfy the constraint. It may be that it's unbounded. We had an example when you asked a question before the break. One of the formulations of the problem with t was unbounded, so the minimum was minus infinity. So that's exactly what it means here. If a problem is unbounded, that means there is no true minimum, and we say in that case the optimal value is minus infinity. So we can always find an x that satisfies all the constraints, and when f of x is less than any arbitrary number m. So feasible means the mean is plus infinity, unbounded, the mean is minus infinity. Here, right. Now, given this, the Lagrangian in this notation, this is where the definition of the Lagrangian depends on the notation. For this notation, the Lagrangian is, the idea of the Lagrangian is to remove the constraints. What is difficult in optimization is when there are constraints. If there is no constraint, we know that an optimal point is obtained by setting the derivatives to 0. Or at least a local minimum and a local maximum will have all the derivatives equal to 0. So if the problem is convex, there's a unique optimal point. So by setting the derivative to 0, we obtain a solution. But when there are constraints, it's more complicated. Observe here that constraints can appear in two forms. They appear in those f and h. For some reason, Bode and Van der Waals don't use G, because we'll see G will come up somewhere later, F and H, but they also appear in X. I'm assuming X is a set which may also contain some constraints. So I differentiate the constraints between those that I want to formulate as inequalities or equalities and those that I keep. Then the Lagrangian is the problem that I obtain by removing the constraint and replacing by a penalty. Instead of saying a hard constraint, I want f to be negative, I pay a penalty for f of x. I also pay a penalty for h of x. H should be equal to 0, and I pay a penalty, and the penalty is multiplied by lambda and nu. For every constraint I, there is a lambda I, and every constraint hj, there is a nu j, and that is the problem, the Lagrangian is this thing here. Now, if we solve the problem where we replace the objective function by the Lagrangian, we obtain another problem, which is called the problem with respect to, which we call this problem L, which has now two parameters, the lambda and the nu are parameters of this problem. So I can minimize this. We call this the unconstrained problem, although there may be some constraints in X, but we have removed the constraint that are explicitly written here. So if I consider this problem here, the dual function of it is the optimal value with the same convention as before. If the problem is not feasible, which means if X is empty, now there's no constraint, so this will always be feasible, typically. And but the minimum might be minus infinity here. So that's the classical thing that is very often done. I have a problem with constraints. I put the constraints into the objective, and I solve the problem with the constraints in the objective here. What I obtain here is called the dual function. Function g is the optimal value of this. Now it depends on the parameters lambda and nu. For every lambda and nu, there is a dual problem. There is an associated problem here. The optimal value of this is what I call the g function of lambda and nu. Lambda and nu is minus infinity if the problem is unbounded. So the domain of definition of g, for g we exclude for all the functions f and h, and fi and h, we do not allow them to be infinite. So here the domain of definition of g is gamma, is the set of lambda and nu such that there is a minimum which is finite, so it's bounded from below. Right. Observe here that we always, by definition, we always force lambda to be larger than or equal to 0. Lambda is the multiplier associated with the constraint with inequality here. And then the dual problem is finding the maximum of this minimum over all the Lagrange multipliers here. So there are many intuitive ways to derive that, but I think the important thing is to have one set, one formalism where this is always the same. So with this formalism, you can do everything that has to do with optimization and duality. You don't have to learn that by heart. For the test and for the exam, we will give you some cheat sheets, which we call the exam booklets, that are already on Moodle. So if you go to Moodle, you can see exactly what are the things that we will give you. We don't trust you, so we don't believe that if you print them, you will not write other things on it with invisible ink or whatever, because you're very smart. So we will print for you this thing here, but you know you don't have to learn that by heart. Although I recommend learning that once for all, because in your entire life, this will be useful. This is really everything you need to know about duality. In fact, here is everything you need to know about duality. It's written in small caps. And what I will ask you to do is to apply this to a simple example that I give here. So here's a small problem. Minimize ax plus by, so a linear function of x and y, over the constraints in a disk, x squared plus y squared less than c, where c is a positive number here, right? And a, b are not both zero here. And we'll ask you to solve it by all possible ways that are given by the theory of duality. That will give 4 different ways four different ways of solving it here. What are those 4 different ways? Well, they are given by all those things here. The first result is that for any optimization problem written in this form, the optimal of the dual is less than or equal to the optimal of the primal, with all the conventions we said before. If a problem is unfeasible, and if it's a minimization problem, then its optimal value is how much? Plus infinity, right? For max, it's the converse. If you have a maximization problem that's unfeasible, its optimal value is minus infinity. So this is true for all cases here. Right? So that's called the weak duality result. It's true for any optimization problem, and it's elementary to show it. It's fairly simple to show that. What is less elementary and is the strong duality is the following. If the problem is convex, and in practice, that's practically all convex problem. In practice, however, and that's the embarrassing part of duality theory, it's not sufficient to be convex. There are always corner cases where the theory doesn't apply. So you need something called constraint qualification. For example, one of them, those are sufficient conditions for strong duality to hold. For example, the problem must be feasible, and there must be at least one feasible point where inequality constraints are satisfied strictly, or, and this is what we will use very often, there is at least one feasible point and one inequality constraint is affine. Affine means linear plus a constant. So for linear problems, if the problem is feasible, constraint qualification always holds. Right? Then, roughly speaking, if we have a convex problem with linear or affine constraints, then all those 4 results hold. Strong duality holds, so there is no gap between the two. The optimal of D is the optimal value of P. To solve the optimization problem, you can relax the constraints and take the optimal values of the Lagrange multipliers, lambda star and u star, which is at this point not very helpful because we don't know the optimal value. But if for some reason somebody gives you the optimal value lambda star and u star, you solve this problem. Now there is no constraint here. That will give you exactly the optimal value. Another constraint is that at the optimal, remember Fi is the inequality constraint. So only 2 things can happen at the optimal. Either the inequality constraint is strictly satisfied, and if that happens, the Lagrange multiplier that corresponds must be 0. Or lambda is non-zero, and then it must be that the inequality constraint is an equality. It's a very important thing to remember. If the Lagrange multiplier associated with a constraint is non-zero, that means that this constraint is active. Active means we reach the constraint. And something very useful is that if all functions are differentiable, a necessary and sufficient conditions for a point to be optimal, x star lambda star, is this constraint here, this combination called complementary slackness, and that, which is the equivalent of saying the derivative, the partial derivative is equal to 0. So this is the partial derivative of this problem here. They are called the Karush-Kuntuker conditions. They are very often used. So if you want to find an optimal point, you write this, you have equations to solve, plus you have to look at complementary slackness. Then there is a completely different type of result, which is called the saddle point result. If you try to solve at the same time two problems, you try to find x that is optimal for some problem where you've removed the constraint. You take the Lagrangian of the problem, you replace the cost function by the Lagrangian, and you solve the problem with this instead of the original problem. Of course, if you take any lambda and u, that will not work. But if you find lambda and u such that the point that you obtain, x star, satisfies the constraint, so x star is found as an optimal solution of the problem where I've removed the constraint. Now, for every lambda in u, I can do that. If I can do that for every lambda in u, then the technique is find lambda in u such that the optimal solution of your problem satisfies the constraint of the original problem. If that happens, then you have found an optimal solution, x star. By the way, you have found an optimal solution, x star, and also lambda and u star of the primal and the dual at the same time. Right? It's called a saddle point of the two. All of those things give you different methods for solving a problem. So for this problem, I will ask you to solve it exactly, because that's a problem that's easy to solve. So if you can solve it exactly and find the optimal dual variables by simply looking the native definition of the problem. You write the dual problem, you write the optimal problem, and you find them exactly. Now you can, once you've written the dual, you can solve it and rederive the solution of the problem by using result 2i, which is this one here, right? If I solve the dual and strong duality holds, then the two have the same optimal value. And also, they are related with the two, right? So you find the optimal value. You can find also the, having solved the dual, you can solve another problem and find the primal. You can also use the saddle point thing that we've seen before. So we will not do that now. It requires 1 or 2 hours to do it, depending on how much you know already of Lagrange duality. I recommend that you do that before the lab. And if you've done that, I'm sure you will appreciate that all this gives different ways of solving the same optimization problem, which is the core and the bread and butter of optimization. Why is it important for us? Well, once I have solved the OPF and write it in a form that is a convex problem where strong duality holds. So typically, this is done, for example, when we have linearized the problem with one of the two methods I've shown before. Then, once I have linearized the problem in this form, I can compute the Lagrange multiplier because, sorry, I forgot one point here. One of the physical interests of this is beyond a technique to solve for optimization problem. Another thing is the interpretation in terms of shadow prices. What is that? Well, if I look at the problem in this standard form, I can parameterize it with respect to the right-hand side of the inequality. So I look at the problem where I vary the constraints. For example, the constraints for us are the ampacity of the lines, the capacity of the generators. Like I said, for every value of this, there is an optimal C, an optimal cost. I call C of uv the function that maps the constraint to the optimal cost here. Then there is this result that the derivative of the cost with respect to a constraint is exactly equal to the Lagrange multiplier. In fact, in this notation, to minus the Lagrange multiplier here. Which means that if I add a small epsilon to the ith constraint, then the cost will decrease by minus lambda epsilon. So that's interpreted. This is the price of the constraint. If I'm willing to get more capacity on the line, how much would it cost for me? Well, exactly lambda I. If I want to increase the capacity of the line by epsilon, the cost of my problem reduces by lambda I epsilon. So the price of a small increase epsilon is exactly lambda I, right? The hidden price of this constraint here. This is how we can translate a constraint, which is an inequality, into a price. And it's called a shadow price because it's not a real price, it's in the shadow here. But this constraint is in fact imposing a price on our problem, which is given by that. And this is exactly what electricity markets and transmission grid operators use. First, we linearize the problem to make everything affine, typically, so that strong duality holds. And now we ask the question, what is the marginal price of our, typically this is the price of generation here. So what is the derivative of the optimal cost of my problem with respect to one of the constraints here? For example, with respect to the load at bus number 1. So what's the derivative of the cost with respect to the load? Well, by the law of total derivative, typically the constraint here will depend on the load in a way that may combine different things here. So dc over dl is the sum of the dc over du and dv times du over dv, which gives exactly this formula here. So this is the formula that is used by operators to compute locational marginal prices here. And I will steal 2 minutes of your lunch break to look at this example. So this is the DC approximation I did on this grid. We have solved it. This is exactly the result we've seen an hour ago. Here, I've plotted all the Lagrange multipliers that are returned by MATLAB, or any linear program solver will give you the Lagrange multiplier that will correspond to all the constraints. For example, I have here 3 constraints, and I will have 1 Lagrange multiplier for each of them. I call them nu. Here are the 3 Lagrange multipliers that I've obtained here. Nu1 is this value, nu2 that, nu3 this. From this, I can compute the locational marginal cost, which is how the derivative of the constraint with respect to L1. Now, the constraint here, U2 and U3 don't depend on L1. U1 does, and it depends with a minus sign. So the locational marginal price is the dc over dl1, which is minus the Lagrange multiplier, which is exactly this here. So we will find that the Lagrange multipliers, in this case, are exactly the marginal prices here. Here we find there are other constraints. There are constraints on the power flow on the lines here. And if we combine them in all the cases here, we also have that the angles must be between minus pi and pi, and that those are constraints of the generation. If I sum up all of those, I find 16 constraints, and I find that they're all 0 except this one and that one. And that one, that's the constraint that corresponds to P23 max here. What does that tell us? Yes?
The constraint is active.
Yes, it means the constraint is active. That means the line 2,3 is reaching its capacity and also generate a G1 here. And those are the only 2 constraints that are active here. So we could compute the marginal cost of an increase in the line G between 2 and 3. Voila, that's all we will do for today. Now, your job is to, if you are not extremely fluent in duality, to go through the exercise I gave a few minutes ago. I will post the solutions later tonight, so you can check your solution against the solution I will post. And then you can practice all of this in the lab to compute dispatch plan and unit commitment plans.